Hello, I'm Dr. Taylor, and welcome to Dr. Taylor's Pedagogical Notes. Right now we're going to look at dividing rational numbers, fraction divided by fraction, okay? And I think you all have a little 1, 2, 3 word thing. I don't want you thinking about that. I don't want you teaching that. I want you doing that. I want you to drive them through this understanding and have them play with it before they learn the algorithm, okay? And it's not easy. This one's tricky, okay? But it's doable, and play with it, and take time, and explore it together. And don't be afraid to not be perfect at it, right? Let yourself show your vulnerability in the room. Model imperfection for them. Let them understand it's okay. And do it with a smile. You know, when they catch you making a mistake, don't be angry. You caught me, you helped me. Thank you for fixing my mistake. Right? Okay. Again, we're going to go from abstract to concrete, concrete to abstract, et cetera, et cetera, et cetera. There are the links, and let's get going. Concrete. Again, I'm using a geoboard, just as a good model for rational and its numbers, and it's just the one I stuck with for all 4 of these videos. All right, so it's going to talk to you about how you use it with rubber bands and all that. I'm going to blast through that, and we're going to get right to the 2/3 divided by 2/5. We're going to build the fractions. So first, I'm looking at the denominators, 3 by 5, right? Okay, I'm looking at that, and I'm going to grab a green rubber band, and if you don't have colored rubber bands, it's okay. Grab a rubber band, right? The outside perimeter one is 3 by 5, 3 by 5, because my denominators are 3 and 5, okay? So next, I'm going to divide it vertically, and I'm going to divide it vertically into thirds, and that's the first fraction. And the 3 is that way. I couldn't divide it into thirds this way, right? Okay. So if I divide it vertically into thirds, okay, there's my 3. And then I'm looking at working with a rectangle of 3 units wide and 5 units high. I'm going to go ahead and put in my blue rubber bands and divide it into fifths, because again, the second fraction was fifths. That's 2/5, right? And then there's the fifths, all right? So now we need to do both geoboards. So this, again, we're back to each student having one geoboard. I'm sorry I didn't mention that up front. Each student has one geoboard, just like the addition and subtraction. So now we're going to go ahead and do this. Does order matter? It's something we can play with and discover for ourselves. I'm not going to tell you. You're going to find it out. All right. Is 6 divided by 3 the same thing as 3 divided by 6? Take some time, discuss it. I'm going to say hit pause because I'm not going to click the timer here. Okay, so we're back. And you discovered what you discovered, and I'm not going to say it on here because it's part of a classroom discussion. All right, so now we have both geoboards in view. Both fractions are represented, but not the numerators. Okay? So let's take a look at the divisor. What's the divisor? The divisor is the one that tells me how many partitions. So here's the weird thing. Like when we did a number divided by 3, we said, oh, we're going to have 3 cups. And we're going to put pieces in each cup and see what each cup holds. And that's one partition, and they all hold an equal number. So 3 equal partitions is this. Well, now we're going to partition them into 2/5. Well, how do I put a 2/5 of a cup and then distribute stuff into 2/5 of a cup? So that concrete example of putting them in a cup goes away with division of rational numbers. So what we're going to do is we're going to try to figure out a way to make that partition become a 1. How many will go into the 1 partition, okay? And so let's look at how we'll do that. So first thing we're going to do is we're going to have the small intellectual dilemma I just discussed, okay? So we need 2 parts in the first fraction. Let's fill those parts, okay? So I didn't put them right next to each other. That's 1/3, 2/3. But I got the nickels, right? And nickels and pennies is what I used. Could be anything. So notice it did not matter which third of the pizza I chose to eat. I still ate 2/3 of the pizza, okay? Now let's look at fraction 2. Of course, I'm going to do 2/5 of it, so I can put them anywhere. There's 1, 2. So now I've got 2/5 represented there, okay? Now here's where it gets a little weird. All right, so now the way I'm going to build anything is as I build it out of units. So if I wanted to build a 5, I would build it out of 1s. I would go 1 and 1 and 1 and 1 and 1. Or counting up to be 1 and 2 3, 4, 5. And that will be how I'd build a 5. Well, if I'm going to build up a 5/5 out of a unit of 1/5 in the same manner, because 5/5 is a whole, and I'm trying to get my second fraction to be a 1, and then change the first fraction to what it would correspond to as a ratio. Okay, so let's see. Here I have 2/5. Now, I don't want to add 2/5 together, because 2/5 is not a unit fraction. A unit fraction is a fraction with any denominator, except 0, of course, and a 1 as the numerator, one of the pieces. If it's cut into 10 pieces, I'd have 1/10, and then 1/10, and if I got 10 of those, I'd have 10 tenths, right? So I want 1/5. How many do I have, though? What? I don't even have to think about it numerically. I can look and say, well, if I want 1/5, where is 1/5? 1/5, okay, this is going to talk a little bit on the slides, my bad. 1/5 is going to be, there we go. 1/5 is going to be right there, okay? Now, you can go back and look at the slides presentation, and all that did was talk about what I said to you already in a different way. I made it easier with words, I think. So that's 1/5. How much of the total nickels do I have there? What piece, right? What did I do to 2/5 to turn into 1/5? I cut it in what? Can you see it? I cut it in half. I divided it by 2, right? There was 2/5. I divided it into 2 equal pieces to get 1/5. Does that make sense? All right. So since this 1/5 represents half of 2/5, right? Then the 3 by 5 is 15, right? I have an equivalence. This is 1, 2, 3 out of 15 pieces. Now you can think of it as fifths or 15ths. It doesn't matter. What I want you to see is that's the same thing. 1/5 is 3/15. 2/5 is 2 of those. 3/5 is 1, 2, 3 of those. 4/5, and that's what we're doing. We're taking it down, but we got to look at what we did. We cut it in half to get it to be a unit fraction. That's the important part. That's the part that's going to mess with people's head if they forget to do that. Okay? So since I cut this in half, I need to cut my other fraction in half. So if I just draw a line through it. Okay? And I look at it, 1, 2, 3, right? But since it's cut in half, I have 4, 5, 6 partitions now, not just 3. All right? Cut it in half. I've got 1, 2, 3, 4, 5, 6 partitions, right? So how many sixths? Right? Well, let's look at that. So 2/6 is what I have here. Okay? Half of 4/6 is 2/6. Just like 2/5, right? So when I cut it in half, 1/5. 4/6, when I cut it in half, is 2/6. So when I look at what I represent here, I am saying now that 2/6 correlates to 1/2. 2, instead of 4, just the 2. 2/6 correlates to 1/5, I should say. So when I do this, to make 1/5 into 1, how many fifths do I need? And again, I told you this would be a little bit convoluted, so sorry. So I need 1, 2, 3, 4, 5 of them, right? So that means I'm going to do 1/5 and 1/5 and 1/5 and 1/5 and 1/5 to bring it all the way up to the 1. Remember I said I wanted to make the divisor worth 1 and see what that corresponded to here. Because I saw that 2/6 corresponded to 1/5. I want to know how many 6 corresponds to 1 whole, or 5/5. So what I do with this, I said there's 1, 2, 3, 4, 5 of them. Remember, repeated addition is what? That's right, multiplication. So I did 1/5 times 5, yes? So what I would do is 2/6 times 5, right? So I did 5 of the 1/5, therefore I want to do 5 of the 2/6 as well. Well, if you think about it, I can skip count like I did. 1, 2, 3, 4, 5. I was counting units. But now I'm counting what? 2/6. So I can skip count. 2, 4, 6, 8, 10. Right? So what I have now is to change that ratio to 1, I have to change the 2/6 to 10/6. Right, you see it? So it's hard to show on the geoboard here, but I'm going to have multiple pieces because 10/6 is an improper fraction, which is like a mixed number, right? And we're going to look at mixed numbers next. But unfortunately, there's only one way to look at this, and it involves a mixed number almost always whenever I'm looking at these rational fractions. So this is a little bit difficult to do. You don't expect a kid's going to be doing this strategy, but what I want him to see is I'm making a ratio, and then I'm taking that ratio up until one of the numbers are friendly. And the other number becomes what it becomes because I'm doing the same thing to both sides. I had to establish that initial ratio, though, right? And then we can look more at that and play with that in class, okay? All right, so what I have is now 10/6 is worth one whole piece, right? So now I would be finished, except 10/6, it's hard for me to get my head around, right? So what other way could I write 10/6? And we talked about it, right? So we could write 10/6 in a different way, yet equivalent, right? Notice this. What happened? Those were both even numbers. So can you see why I chose to try to divide them by 2? Or an easy way to think of it is in half. I like to think of halves and doubles. That's what we do in elementary school, halving and doubling, tripling and thirding. But halves and doubles, right? Half of 10 is? I can say, what's 10 divided by 2? And a kid will, I'll say, what's half of 10? They'll say 5. They get halves. Halves is like, boink, pops out. So what's half of 10? And what's half of 6? Okay? So 1 really correlates with 5/3. So 2/3 divided by 2/5 is 5/3. Notice that I divided by a number smaller than 1 and my value grew, right? If I divide by a number smaller than 1, my quotient will grow. There's an inverse relationship. If I divide by a number bigger than 1, my quotient will be smaller, right? For instance, what's 15 divided by 3? 5. 5 is less than 15, right? But 15 divided by 1/3 is 45, which is more than 15. So when I divide by a number larger than 1, my quotient will go down, right? And so dividend divisor quotient. So that's the way that works. So if this number is less than 1, my answer will be larger than that. If this number is more than 1, my answer will be smaller than that. 5/3 is definitely more than 2/3, right? And 5/3 can be simplified even farther. What would 5/3 become? Well, that's for the mixed number part. Okay? Graphical representation is the same. I'm not going to belabor it much. There's that, there's that. This will be a little easier to do than the geoboard one, though, when you look at it. This is going to make a little more sense when you look at it. Geoboard one was weird because you cut through the middle of the nickels and you, wait, where'd those go? And I'm sure you were thinking that. This will help to clarify that. So sometimes, you know, maybe the geoboard was a poor choice, but, you know, it's what I could think of. So let's look at this, comparing our partitions to get equivalence. Then I enumerate my things, right? And I say, okay, I want to have just divisions, right? I want to have just one of these pieces, so I'm going to cut that green part in half. If I cut one side in half, I have to cut the other side in half, or it won't be equal. If I cut both parts in half, then each person still has an equivalent portion respective to one another. They both have half of what they had before, but no one is better off than the other one. They just each have proportionally less. So when I cut this in half, right, that gives us 1/5. And so I must cut the 2/3 in half. Bang. Now you can see it's so much easier with this area model. There's 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, right? But what's the half part of 4/6? You see the half part? It's 2 out of 6. So when we did the, and I think I even got myself caught up in it, when we did the geoboard model, we want to count those nickels or those dimes or those pennies. But when we do the area model, it's a little bit, I think, a little bit more clear. There's no dimes or objects to count. It's a shape. It's cut in half. Now the shape has only 2 pieces in the bottom half of the possible 6. So 1/5 corresponds to 2/6. So I could write that as 2/6 colon 1/5, right? And I'm going to put them in that order simply because that 5th was in the back, and I want to keep the order the same just in case that matters. And if I can't say for sure whether it does or not, I'm going to assume it does and operate under that assumption totally. So again, how many fifths does it take to make a 1? Because that's what I want. I want to turn this into 1. It takes 5 of them. So 5/5 will correspond to 5 of these 2/6, or 5 over 1 times 2/6. You can do that, right? Or you can go 2/6 and 2/6 and 2/6, which will give you 10/6. However you want to do it, okay? So what we see is 10/6 can be simplified because the n divides by 2 and the 6 divides by 2. So 10/6 could be written as 5/3 by dividing by the common factor. So I've got a simplified statement of 5/3. 5/3 corresponds to 1. So 5/3 is in every 1 partition. That's what it's saying to you. That's why this method is explaining what division is. But let's face it, boy, it's kind of convoluted and it's not for everybody. But it is a way to put some concrete and some graphical understanding under the kid's belt about what division means. What does it mean? It means divide things into partitions. But when my partition is smaller than 1, I can't get my human head around it. So I get a ratio of relationships, and then I multiply that up until one side of them is 1, and I can compare that corresponds to 1 partition. 5/3 of a pizza goes into every 1 partition. Okay? Abstract. You're thinking about it. You can imagine the partitions. You can use the algorithm, but in the end, until you do enough of them to understand it, it won't make sense to you why you might keep, change, flip, right? Or invert and multiply. But in the end, if you play enough, the division makes sense, and then the algorithm will become easier for them to remember it because it'll make sense to them. Okay? All right. And so that's that. Thank you very much, Division of Rational Numbers. I look forward to seeing you in the next number of problems.